Sir, we are live now, sir.
Hello, everyone.
Sir, we are live now, sir.
Thank you. Hello, everyone. A very warm welcome to this first session, live session.
Hello, everyone. Sir, we are live now, sir.
Thank you. Hello, everyone. A very warm welcome to this first session, live session.
Hello, everyone. Sir, we are live now, sir.
There was some echo there.
Hello, everyone. A very warm welcome to this first session, live session. Hello, everyone. Sir, we are live now, sir.
There was some echo there. Okay, we'll get started now. So thank you for joining this first session, first live session of Introduction to Photonics. I see there are about 1,000 people enrolled in this course. I thank you for your interest, first of all. Very good evening, first of all, to all of you that have tuned in. So this course actually is something that we conceptualized several years ago, essentially to bridge the requirement of industries, the photonics industries, and what is taught in high school. So we actually offered this course in IIT Madras initially for several years, fine-tuned the content. And the last 3 years, actually, we've been offering it for NPTEL through the Swayam portal now. And so there have been good feedback on the course since it's dealing with some of the fundamental aspects of photonics. A lot of people that are from a non-photonics background are able to take this course and benefit from that. And I hope you have the same benefit as well as you go through this course. Now, from what I understand, you've already been through a couple of weeks. This is probably your third week of lectures that you have been exposed to. And you have an assignment that's due this week in a couple of days, actually. And this is basically assignment 1 and 2 as far as the course is concerned. And from what I understand, or what I know actually, the assignment 1 and 2 are focusing primarily on wave optics. We started with wave optics in, ray optics in week 1, where we consider light propagation as rays, which are straight lines of propagation. And we saw through several examples that ray optics by itself is actually a very powerful concept, and we can learn a lot about light and its properties, where it's useful, through just considering it as ray optics itself. And then we looked at towards the end of the first week, we said ray optics is fine, but it does not explain certain principles. For example, we said the principle of diffraction, for example, the bending of light around corners, that is actually not something that is explained using ray optics. And so we actually introduced light as light propagation as in waves. And once we started tracking light as waves, we had this very important property of light that come into the picture. We said we can actually now track the phase of the light wave. And once you track the phase of the light wave, there are some very interesting principles that we are getting exposed to. And prominent among those principles is interference of light And so we saw examples where diffraction of light along with interference of light can cause some very interesting properties. It can make light disappear in certain locations, and it can appear in certain, or appear more strongly in certain other locations, and so on. So there was this classic example of Young's double slit experiment, through which you learn how constructive interference and destructive interference works, essentially when the light paths are such that the accumulated phase is integral multiples of 2 pi, 0 or integral multiples of 2 pi, we get constructive interference. And if it is odd integral multiples of pi, then we said, you have destructive interference, which is essentially cancellation of light, right? So that was rather interesting, and we saw different configurations through which this interference can happen. It's typically through an apparatus which is known as an interferometer. We saw that although you can call the Young's double slit itself as an interferometer, you have very specific types of interferometers. We looked at differential path interferometers, or common path interferometers. So differential path interferometers, primarily we looked at examples of Michelson interferometer or a Mach-Zehnder interferometer. And then for common path interferometers, we looked at a Sagnac interferometer or a Fabry-Perot interferometer. So we learned how to dissect these configurations to the point that we can understand the interference phenomena that's happening in these interferometers. And we also recognize that these interferometers can be very useful to measure some physical quantities also. So we looked at possibly measuring changes in the refractive index inside this interferometer, inside one of the arms of the interferometer. We looked at possibly using this interference principle to describe how different colors separate out in the different interference orders. And of course, that also gives you the idea that the interferometer can actually act like a filter, a color filter. So you can pick very specific colors by this interference principle itself. And then lately, we've been talking about the concept of coherence of light, which is essentially how light correlates with itself, right? So we talked about something called temporal coherence, where one wavefront is propagating like this, but one wavefront is actually correlated with a delayed version of the wavefront. And we wanted to see if there is any correlation existing. And then we define something called correlation length, wherein we say it's only over a certain length that this correlation holds good. It gives you a good value, but beyond a certain length, this wave does not have memory that it came from the same source compared to this other wave, and so the correlation actually breaks down, or the coherence is limited. So that is what we called as temporal coherence. But then we also looked at this other coherence, and of course we said the coherence length is inversely proportional to the line width of the source. So broader the line width, if you have broadband light consisting of all this multiple colors, like for example white light will have very low temporal coherence, or the coherence length is going to be very short. Whereas if you go to a laser radiation, which consists of frequencies only over a very narrow band, in that sort of, it's a very narrow spectrum that it possesses. In that case, the coherence length was actually much longer. So you could essentially measure the coherence through something like a Michelson interferometer, where one of the arms you can actually delay with respect to the other arm. And as you delay, you can actually see how the coherence actually, or the resultant interference actually fades out, right? Through that, you can actually measure the coherence length and the coherence time also you can infer from that. So that is one type of coherence. The other type of coherence is describing how directed the light is. If the light beam is actually having wave vectors in multiple directions, or all these directions, they are not in phase with respect to each other, then that's actually a very poorly spatially coherent light. And you can once again look at the example of the fluorescent lamps through which we can get light. That is actually just spreading over different regions, and they're not in coherence with respect to each other. Whereas you can have a highly directional beam, for example, once again, a laser beam, which actually has wave vectors only over a very narrow range of angles. And in that case, we said the spatial coherence of that source, which is not going to be very much diverging over long distances. So that is actually highly spatially coherent, right? So we learned how to distinguish between temporal coherence and spatial coherence, and we learned how to go back to the properties of the laser itself and say, or properties of the light source, to say, how can you quantify temporal coherence? Temporal coherence is quantified with respect to the line width of the source, and spatial coherence is quantified with respect to the angular spread of light coming off that source. Okay, so we recognize those sort of concepts, and we, of course, we have been also having lab demonstrations, separate videos, where one of the TAs is demonstrating a concept relevant to the material that has been taught in week 1 and week 2. So hopefully you've been tracking that. One of the things that we noted from our previous set of students is people actually pay attention to the lectures, but not so much the lab demonstrations. And one thing that we have done to address this issue, we do want all of you to go through the laboratories videos also, the demo videos, and to give you some credit for watching those videos. What we have done is, in our assignment problems, we have been including 1 or 2 questions from the lab videos. So hopefully that will motivate you to go through those lab videos. And the lab videos, the way they are designed is actually supporting the lectures in a fairly coherent manner. It's one thing to see these concepts being taught through the lectures, but it's quite another to see them actually be brought out through physical experiments. Unfortunately, you cannot, in IIT Madras, we have a course where you can actually practice some of these experiments yourself on a weekly basis. So, you learn something in theory and then you practice that on the same week. Unfortunately, you cannot do that since this is an online format that we are interacting. But nevertheless, the closest thing that we could do is to demonstrate that experiment to you so that you can benefit from that. So please do watch those videos as well, and hopefully that will be useful in understanding some of these concepts. And the other aspect of this is, it is not like a once again a physical medium where you can actually get your doubts cleared right away, in class. So that's not the kind of format that we are in. But nevertheless, we have this discussion forum, which some of you have been using. I can see regularly you're asking some questions, but and we are trying our best to answer them within a day or two. But I would like to see more of you actually participate in asking questions through the discussion forum so that we can have a sort of interaction going on. It's when you ask a question, it's not just educating yourself, but you are actually prompting others to think about certain concepts as well. So please don't feel shy about asking any questions. No question is a stupid question, and it will be only to your disadvantage that you limit yourself from asking a question just because you think this may be a straightforward thing. Believe it or not, most cases, the doubts that you have is actually consistent with doubts that several other people would have in the course. So please go ahead and use that discussion forum to keep interacting with us. Now, the other forum for interaction is this live session wherein I can address some of the queries that you have, and thanks to NPTEL, they have actually made this happen, and they've also opened up some spreadsheet where you can actually ask questions, and so I will go ahead and try to answer those questions now. So one of those questions is actually, is maximum transmission means constructive interference. So it's one of the questions I see here. And yes, that's what we are saying. Constructive interference gives rise to high transmission of light. If you're talking about, for example, an interferometer, let's say even a simple Young's double slit experiment, wherever you have constructive interference, that's where the fields are adding with each other, and the fields corresponding to the individual wavelets are adding with each other, and that corresponds to a maximum intensity in those regions. And that holds good for other cases also, for a Mach Zehnder interferometer, Michelson interferometer, or even a Fabry-Perot cavity. Now, the question is actually whether it's maximum transmission. Now, maximum transmission, you will have to be careful about quantifying that. It is corresponding to addition of the fields, but depending upon the strength of those fields, you may have, in certain orders, like zero order typically is where maximum intensity is present if you in a simple Young's double slit experiment, which is illuminated with a light source that's normal to the slits. But if you go to the first order and second order and so on, there could be a reduction in the intensity of the light that purely depends on how much diffraction is happening at the slits and what is the component of the electric field that is actually present at a particular location. Okay, so just to summarize what I was saying, yes, constructive interference does mean high transmission, but whether its maximum corresponds to the distribution of the fields at the plane where you're observing the interference. Now we'll move on to the next question. Next question is, which interferometer will give accurate refractive index for any new material, say any analyte? Or in other words, which interferometer can give rise to accurate measurement of the refractive index of a material, of an unknown material? So that's certainly a good question. And I think I touched upon it during the lectures, during one of the lectures. I was mentioning that Michelson interferometer, or for example, even a Mach-Zehnder interferometer for that matter, where you have a differential path. If you put material with an unknown refractive index in one of the paths, then in that path, the phase accumulation is more compared to the other path where, let's say it's all in free space. And in one arm, there is actually a glass slide, for example. Then that arm is delayed with respect to the other arm. And that delay is now causing a change in the intensity at the output. And by calibrating the interferometer for this change in intensity, now you can actually figure out how much would have been the phase delay. Now, one thing that you have to keep track of is the phase delay or the change in intensity is going to be the same for multiple values of phase delay, or every 2 pi of that phase delay, the intensity is going to be the same. So your accuracy with which you can measure your sample refractive index is limited by that. You cannot actually measure over a very large range, because over that large range you may actually have multiple constructive and destructive interference cycles. So that is one constraint. But nevertheless, Michelson or Mach-Zehnder interferometer is one of the more commonly used apparatus for sensitive refractive index measurement. Okay. So those are the questions I see in my Excel sheet. Now I'll go on to the chat box and see if there are any other questions. And I see that some of the TAs, Vishwanathan and Anand have been actually trying to answer some of the questions already. Thank you guys for pitching in. So there's one question where it says, is blue color is difficult to generate, as in the case of blue LED, I think that's what the question is. So blue color certainly corresponds to short wavelength in the visible region, and short wavelength means higher frequency compared to other colors like yellow or red or green. So if it is high frequency, we know that the energy of a photon, energy of light in general, we will come back and define that a little later. We will say that corresponds to h times nu, where h is the Planck's constant and nu is the frequency. So lower the wavelength, higher the frequency, and higher the frequency, higher the energy. So you can say that blue, and then if you go to even lower wavelengths like ultraviolet wavelengths, you're going to have high energy radiation. And higher energy radiation, in general, it's a little more trickier to generate compared to, I wouldn't say it's difficult, but it's trickier. It requires only specific materials. If you're talking about a semiconductor, it requires a material with very large band gap energy. These are some of the specifics that we will get to in the next few weeks as we move on. But the short answer is yes. Generating blue light from a light source requires a very specific type of material, and you have to take care of certain things while generating that. We'll come back and look at that a little later. So the other question is, by calculating V number, we can tell if the fiber is single mode or multi-mode. Yes, that is very much true. So the V number, especially V number of 2.405, why am I saying that particular value? Because 2.405 corresponds to the first zero of the zeroth order Bessel function. And so that corresponds to the cutoff of the fundamental mode in an optical fiber. So if V number is greater than 2.405, then you have the next higher order mode also getting excited. So you will start getting towards the few moded and then the multi-moded regime. But if you are if your V number is less than 2.405, then you can have only one mode propagating in the waveguide. So that's why it is called a single mode waveguide. Okay, hopefully that is clear. Then after absorption, the photon spends some time at the excited state. That is a photon lifetime. So it is like every photon spends this time more or less. So the question is, yes, we talked about, I think, absorption of light maybe in the fourth week of classes, fourth week of lectures. Maybe some of you are watching these lectures ahead of the regular lecture schedule. Nothing wrong with that. Appreciate that. So the question is related to the excited state lifetime. And so we will have to clearly define what the excited state lifetime is. I think I mentioned this in the lecture also. So you excite an atom to a higher energy level, and from that energy level, it comes back to it's actually a metastable state. So from that energy level, it comes back to the ground state, and when it comes back to the ground state, there is a possibility that it emits a photon. Now, when it comes to the ground state, is not deterministic. So even when we say, let's say the excited state lifetime is 1 millisecond, if somebody is telling you that, what that means is if you have a collection of atoms at that excited state, if you have 1,000 atoms at the excited state and they're all getting de-excited, 1 over E number of 1,000, right? That many photons will show up within this 1 millisecond time scale. So it actually, the emission or how many photons are emitted, it's actually, it's a probabilistic event, and it goes down as exponential, okay? Meaning the longer events are less probable than the shorter events, shorter emission events. And 1 over E corresponds, where 1 over E of the photons get emitted, that corresponds to the lifetime of that excited state. And that is actually what is called 1 millisecond. So that doesn't mean that the emission will not happen within 1 nanosecond. That doesn't mean that the emission will happen only after 1 second. But the probability of emission happening within 1 millisecond is quite high. You can quantify that probability as well, right? So light emission in general is a probabilistic event. And in a way, that is actually the beauty of light. There is a certain randomness about how light is emitted. And that randomness, the quantification of that randomness is what we call as coherence of light. Okay, so this is something that I think the beginning of that lecture on coherence, I was mentioning that coherence is actually a measure of the randomness of light. And one of those properties is what we are seeing here in terms of the excited state lifetime. Now, this person also has mentioned that it calls it photon lifetime. I want to distinguish excited state lifetime from the photon lifetime. Photon lifetime, from a perspective of a cavity or an interferometer, let's say a Fabry-Perot interferometer, photon lifetime corresponds to the average time that the photon is spending within that interferometer before getting, before escaping that interferometer or before getting lost. So photon lifetime is different from excited state lifetime, right? And let's see, is single mode fiber difficult to create? You can say in some ways it's challenging to create. Once again, I would not use the word difficult because nothing is really difficult. It could be challenging, right? So it's challenging in the sense that if you think about it, a single mode fiber, the size of the waveguide or the core of the waveguide is comparable to the wavelength of light. Since we are talking about light wavelength in the order of microns, the core region is in the order of few microns. And that means you're having to draw this fiber. An optical fiber is typically drawn from a preform. You have to draw this fiber at a very high rate so that you can bring down the core diameter to such a low value. So that could be challenging, but nevertheless, it is something that's done routinely today. 50 years ago, it was a huge challenge, but today, even as we speak, literally billions of kilometers of optical fiber are being manufactured with very, very high precision. We're talking about fraction of a micron precision with which you can generate these waveguides. And so it's not as much of a challenge today as it was before. Right? So that's all the questions I see in the chat box, and I certainly thank you for that. And like I said, you may have many more questions than what's mentioned here. I see there's only a few people that have logged in here, and so that many more people may be watching this later on. So the message to them is, please go ahead and try to ask all your questions through the discussion forum. The TAs are checking that on a daily basis, and I am actually checking that every now and then. So we will be able to address your questions. And if you have any other feedback, if you have feedback as in we want to have more number of these live sessions, we can probably consider that. That clearly depends on how much interest you show towards the course and whether you have material to discuss in these sessions. Okay, so with that, let me close this session and look forward to meeting you all in the next session, which should happen roughly 4 weeks from now. But like I said, if you have a suggestion to hold it earlier, please do let us know through the discussion forum, and we can schedule it earlier as well. Okay, and good luck. One thing I want to mention about the assignments, please watch the videos completely before attempting the assignments, and that is going to be quite beneficial for you. The final exam for the course, where most of your grade is decided there, is going to be based on questions which are looking very similar to what you had in these assignments. Okay. In fact, you may have some of these very questions that you are answering here, that will be asked, that may be asked in your final exam. The big difference between doing it now and doing it then is that you're not going to have it's going to be a closed book exam. You're not going to have the luxury of the videos and the other learning resources while you're doing this final exam. So please keep that in mind. You want to do that with your own effort right now, not discuss with the friends and not copy from somebody else, because that is not going to help you in the final exam. So, but if you, on the other hand, it's okay to discuss with your friends, what is the methodology you use and all of that, just to understand how to go about it. And of course, you're more than welcome to discuss it with us, the TAs, as well as myself. And we are happy to clarify your doubts. But please do make a genuine effort to solve each and every assignment problem, because, like I said, these are the kind of problems that you're going to face in the final exam. We had a lot of situations where somebody scores very high in assignments, and that's because they have been discussing with others and they get all their answers even from others. But when it comes to the final exam, there is actually a minimum mark that you're supposed to get to pass the course. And we find that people are not able to get those marks because they did not do original effort as far as solving this assignments concerned. So please do these assignments sincerely. And if you do this on a weekly basis and you're going to keep improving your knowledge in photonics, I'm sure you'll find the final exam is actually fairly straightforward to deal with. Okay. So good luck with all of that. And until next time, thank you for your attention, and take care.
Okay, sir. Can I stop, sir?